Strong acids versus weak acids. Strong acids dissociate to a great extent and produce many hydrogen ions and have a large Ka. So dissociate to a great extent, produce many hydrogen ions, large Ka. Weak acids are the opposite. They're going to dissociate to a small extent and therefore produce few hydrogen ions and have a small Ka. So if I gave you a couple of different acids, you should be able to identify them as being strong or weak. The first one, given the double arrow, identifies it as a weak acid. The second one, having a single arrow, identifies it as a strong acid. This one, the strong acid, will dissociate completely, producing many hydrogen ions. Also will produce many bromide ions, but being an acid, we focus on that ion. Phosphoric acid is a weak acid. Being in equilibrium, the equilibrium position is far to the left and therefore will produce only a few hydrogen ions. And we can write a Ka for it that will have a relatively small value to it since the equilibrium position is to the left. If we were to write a Ka for the strong acid, which is typically not done, it would be very, very large, usually on the order of 10 to the 4th, 5th, 6th, something along those lines. Given a diagram, you should be able to identify an acid as strong or weak. If we look at the first one, most of the acid is undissociated. There are very few free hydrogen ions present, and that identifies it as a weak acid. And so if I were to write the dissociation reaction for this one, note the double arrow indicating equilibrium, and generally the equilibrium position is far to the left, meaning again, mostly undissociated, very few hydrogen ions being formed. On the right-hand side, note there's only one undissociated acid present. There are many hydrogen ions present. This indicates a strong acid. And if I were to write the dissociation reaction there, here we see a single arrow, meaning the equilibrium position is to the right. Typically, we consider it all the way to the right, with all the acid being dissociated, producing many hydrogen ions in solution. Do not confuse the idea of strong and concentrated or weak and dilute. Here I've got 4 pictures, and 2 of these pictures show strong acids, and those are B and C, because whatever acid is there is dissociated into its ions, and A and D are weak acids because whatever acid is there is not dissociated to a great extent. Therefore, there's few hydrogen ions present. We would describe B as a concentrated strong acid. There's a lot of the strong acid there. C we would describe as a dilute strong acid. It's a strong acid because it dissociated to a great extent. Dilute because there's only a small amount of it there. D we would describe as a weak dilute. Weak because whatever's acid is there dissociates to a small extent. Most of it stays in the undissociated form. And A we would describe as a weak concentrated because it's concentrated because there's a lot of it there, weak because little of it dissociates. So the terms strong and weak refer to how much the acid dissociates. The terms dilute and concentrated refer to how much is present in that solution. If we have a triprotic acid that is weak, such as phosphoric acid, then it will dissociate its hydrogen ions one at a time. So phosphoric acid will dissociate into H2PO4 minus plus a single hydrogen ion. The Ka is going to equal the products over the reactants and is going to have a Ka value of 7.1 times 10 to the minus third. The H2PO4 then will dissociate one more hydrogen to form HPO4 2 minus plus a hydrogen. Would you expect the Ka of the second one to be larger or smaller than the first one? It is going to be smaller than the first one because The second hydrogen is coming out of a negative ion. The first hydrogen is coming out of a neutral molecule, and it's harder to take a positive ion out of a negative. There's going to be a stronger attraction. The point is, each successive dissociation, the Ka gets smaller and smaller, or we say the acid gets weaker and weaker. So the third dissociation, the HPO4 minus, gives up its hydrogen to become the phosphate ion, and the Ka for that one is going to be 4.5 times 10 to the minus 13th. They get significantly smaller each time. Another polyprotic acid is sulfuric acid. It is diprotic. It's a strong acid in the first dissociation, but a weak acid in the second. So if I were to write the dissociation for the first hydrogen ion, we have a single arrow, and we assume complete dissociation into its ions. It's weak in the second one, so now I need a double arrow. And again, I can write a Ka for this one because, again, it's a weak acid and it's products over reactants, giving you this equation. Just as strong acids produce many hydrogen ions, strong bases produce many hydroxyl ions and have a large Kb. Weak bases dissociate to a small extent and have produce few hydroxyl ions and have a small Kb. Identifying the following acids or bases as weak or strong. The first one is going to be weak. Again, note the double arrow, and Kb for this one, it will be products over reactants. And the second one is a strong base. Note the single arrow, so it will dissociate completely, would have a large Kb value, and would produce many hydroxyl ions in solution. If I ask you to identify the following base as weak or strong and is dilute or concentrated, M here stands for some kind of a metallic ion, and the OH is the hydroxyl, making the substance a base. This first one is going to be a weak concentrated. Weak because most of the base is undissociated from the metallic ion. Only a few metallic ions and hydroxyl ions are formed. The second one is going to be a strong dilute. Strong because all the base that is present is dissociated, and dilute because there is a little of it present. And that ends our discussion of strong and weak.